The universe, immensely large, endlessly fascinating. A cosmos of questions which have tantalized man for thousands of years. Generations of scholars tried to explain the incomprehensible. In the search for the origin of matter, the boundaries between science and philosophy became blurred. Over 2,000 years ago, Greek philosophers, attempting to explain the mysteries of nature, hit on a concept that was to change the world, the concept of the atom, the smallest irreducible building block of nature. But evidence of the existence of atoms was a long time coming. 2,000 years later, the natural world was closely observed and was found to obey laws. Natural phenomena could be explained, described, and sometimes predicted. Analytical minds went one step further. Experiments were devised, nature was expressed in figures, modern scientific procedure was born. One of the pioneers of modern science was John Dalton, whose work put the concept of the atom on a scientific footing. Unlike the Greeks, who first suggested the atom's existence, he was not prepared to speculate and leave it at that. With the help of a pair of scales, he set out to discover the laws of chemical reactions. Dalton defined the elements as matter consisting of distinct uniform atoms, particles identical in size and atomic weight. He represented the atoms as circles. In chemical reactions, he claimed, atoms themselves were not changed, they were merely rearranged. How atoms were linked was something Dalton could only speculate about. There was no way he could see them. But even at that time, the size of an atom could be deduced from the thickness of a film of oil. It had to be microscopically small, less than 1/1,000,000th of a centimetre across. The 19th century brought massive advances in science and technology. Man started to make use of what he'd learnt about the natural world. He drilled for minerals and lit up the night. By the second half of the century, he was generating electricity. The train of progress was unstoppable. But when the 20th century dawned, there was still no actual evidence that atoms exist. Many respectable scientists doubted the existence of atoms, and those who believed in the atom had to make do with the weaknesses of an atomic model based on hard balls. Observations were made for which this provided no explanation. What determines the structure of crystals? How are chemical compounds formed? Where do objects get their colour? These questions, and others, remained unanswered. Ultimately, everything pointed to the fact that atoms, despite their name, could be subdivided, that there were particles which were even smaller. In 1897, Joseph Thomson discovered the electron, a particle that is smaller and lighter than the lightest atom. In 1904, Thomson developed an atomic model in which electrons formed elementary building blocks. According to his theory, the atom consisted of a mass of positively charged matter in which negatively charged electrons were embedded, like raisins in a cake. The plum pudding model, as it was known, was of little scientific value, but it did prompt physicists to look more closely at the structure of the atom. Joseph Thomson gathered around him many bright young scientists at his laboratory in Cambridge. Among them, the New Zealander, Ernest Rutherford. In 1911, Rutherford reached a momentous conclusion, based on experiments involving radioactive rays. When gold foil, a material hundreds of layers of atoms thick, was bombarded with positively charged helium nuclei, only a small number of particles were deflected. Most passed straight through the foil. From this, Rutherford concluded that atoms couldn't be solid spheres. They had to consist largely of nothing. Instances where particles actually collided with something and were deflected backwards were extremely rare. On the basis of his observations, Rutherford developed a new atomic model. He postulated that nearly all the mass of an atom is concentrated in a tiny, positively charged nucleus surrounded by electrons. To prevent the negatively charged electrons being drawn to the nucleus, they remain constantly on the move, orbiting the nucleus like the planets in the solar system. But the Rutherford model had a fundamental flaw. According to the laws of electrodynamics, orbiting electrons would lose energy and spiral into the nucleus, so atoms couldn't exist. But we live in a relatively stable world, so the Rutherford model had to be wrong. Where it went wrong was shown in 1913 by the Danish physicist Niels Bohr, who was working at the time at Rutherford's laboratory in Manchester. A more accurate model not only needed to explain the apparent stability of atoms, it also had to show how atoms emit light. It had to account, for example, for the lines in the spectrum of light emitted by atomic hydrogen. This was Bohr's starting point. He ascribed different energy levels to electrons in different orbits. The greater the radius of the orbit, the higher the level of energy. If an electron falls from an outer orbit to an inner one, it gives off energy, which it radiates in the form of a package or quantum of light. Light of a specific frequency, which appears as a clearly defined line in the spectrum. Bohr argued that as long as electrons stayed in their allotted orbits, they didn't radiate energy. He was greatly discomforted by the fact that he couldn't explain his more or less arbitrary assumptions. He could only justify his model by pointing to the fact that it accounted for physicists' observations and provided an explanation for at least the simplest of all atoms, the hydrogen atom. In 1915 and 16, the Bohr model was extended by the Munich physicist Arnold Sommerfeld, who suggested that the orbits of electrons were elliptical. With this understanding of the structure of atoms, it was possible to explain the physical basis of the periodic system of chemical elements. Taking the hydrogen atom as a starting point, all the other elements could be derived by successively filling shells with electrons. The periodic system was thus explained. Periodicity depended on the arrangement of electrons. The political and social upheaval triggered by the rise of the Nazis forced many atomic physicists to leave Europe. Most of the scientists, many of them Jews, fled to the United States. In the course of the Second World War, atomic physics began to lose its innocence. Niels Bohr strengthened British and American resolve to beat the Germans in the race to build a nuclear fission bomb. Atomic physicists were now nuclear physicists. In a massive undertaking, 180,000 people worked on building the American A-bomb. They created the most terrifying weapon of all time. In 1954, not far from Geneva, the European Nuclear Research Organization CERN was founded. 13 nations pooled resources in a joint effort to unravel the mysteries of matter. It's an astonishing fact that the smaller the subject of research, the bigger and more costly the experiments. By this time, it was known that even the nucleus of the atom was made up of smaller particles, protons and neutrons. Now, research was focused on finding something even tinier, the last building blocks of matter. In huge particle accelerators, electrically charged particles, electrons, protons, or light atom nuclei were accelerated to high speed. In some cases, the velocities reached were close to the speed of light. Gigantic magnets kept the particles on course and focused the particle beam. Collisions with other particles provided information about their structure. But more and more people started to ask, what's the point of going to so much effort? One reason is to satisfy human curiosity, to explain the last remaining mysteries of the natural world. But there are others. This kind of basic research has definite practical uses. Superconductivity, the phenomenon of zero resistance to electrical current, has applications in medicine. Superconducting magnets are used in magnetic resonance imaging systems. Laser beams long ago left the domain of the research laboratory and became part of daily life. Laser beams are created when atoms are induced to emit light of a single wavelength or colour. To understand the phenomenon of laser light, we have to look, like Niels Bohr, at the energy contained in the electrons of atoms. Drawn from the liquid melt, a perfect single silicon crystal. We know its electrical properties and we can alter them by doping, in other words, adding small amounts of impurities. In this way, it's possible to create microscopically small zones with specific electrical properties, which enables millions of transistors to be accommodated on a wafer the size of a postage stamp. A technology that's changed our lives and still has untold development potential. Structures are getting finer and more complex, and tools are becoming increasingly precise and sophisticated. We can scan surfaces with needles tapering to a single atom at the tip. With a tunnel microscope, we can actually watch crystals being formed. Layer by layer, the atoms fit together and the crystal takes shape. Using the same technology, we can even make atoms themselves visible. Each little mound here is one atom. All in all, we're pretty familiar with the atom today, and much of the credit goes to this man, the father of modern atomic theory, Niels Bohr.